Continuing. Now we're going to talk about inferences for two means. So here's the ho and the ha. Same thing like the p's. Here's our test stat, but now we're using t because it's means. So the sample means, and then that's always going to be 0 in this course, so it's really just 0. That's the standard deviation squared, so that's the variance, divided by this n1 plus the variance of the second one, or squared standard deviation, divided by n2. We're going to use the calculator's degree of freedom. I said use the degree of freedom on that last video, but proportions don't have a degree of freedom, so just ignore that. But we're going to use the calculator's degree of freedom, where before it was n minus 1. We're never going to pool. And then here is the confidence interval, and this is 2 sample t-test in the calculator, and that's 2 sample t-int. So if I were you, I'd pause it and copy that down. So let's get started. All right, here's a good one. The results of a state math test for a random sample of students taught by 2 different teachers at the same school are shown at the left. Can you conclude there is a difference in the mean math test scores for the students of the 2 teachers? Assume the populations are normally distributed. Yeah. So here's teacher 1. There's that score, 473. There's teacher 2, 459. That lower score, that lower score is probably me, and that higher score would probably be Mrs. Johnson. Because when it comes to state mathematics tests, Mrs. Johnson is the key. Test the claim using a hypothesis test. So here we go. So this is going to be, so mu1 would be my scores for the entire population. This is just a sample of my students, only 8 of them. You know, assuming I had a lot of students, but so are these the same? Or are our scores the same? Or are they different? So that's why it's not equal to. The test stat is x bar 1 minus x bar 2 minus mu1, that's an equal 0, sorry, minus mu1 minus mu2, but that's 0, divided by s1 squared, so 39.7 squared over n1 plus 24.5 squared over n2. All right, beautiful. This is a gorgeous looking formula right here. It's really fun to do by hand, but we're not going to do it by hand. Stat test 2 samp t-test. Well, we don't have data on a list, so x1 473. No. 473. S1 is 39.78. Now Miss Johnson's 459. Or that's actually me. 24.5 and 18. Hopefully I got that right. 473, 39.78, 459, 24.5, 18. And it's a not equal to pool. Never. Never. Some books would tell you to pool if they assume that the variances were supposed to be equal, but it's not really, nobody really does that in real life. At least from the 3 statisticians I know. Calculator, there it is, 0.92. That is only 0.92 standard deviations away, that difference. Doesn't look like it's great enough. Degree of freedom, let's copy that down, 9.46. And p-value 0.38. So how they found the p-value was, all right, so here's 0.92, so I got to go this way and then double it. That'd be 2 times TCDF 0.92 to infinity, comma, degree of freedom. And that's how we would get 0.38. So since p-value is greater than alpha, fail to reject HO. So the mean mathematics scores, test scores, appear to be the same for the two teachers. So the two teachers appear to have the same scores. Now, she's winning on this one, but it's just such a low sample size that if I'm going to infer these results about all of her students, maybe all the students that actually took this test, could be hundreds, and then use my small sample size I picked out of all the students that took that test with me, there's really not that much difference to say she's a better teacher than I am. All right, confidence interval. So we're looking at x bar 1 minus x bar 2 plus or minus inverse t. Okay, let's do, all right, alpha's 0.05, so we're going to do a 95%. That'd be 0.025, comma, use that degree of freedom. What the heck was that? As long as it's not my cell phone, I don't really care. 39.7 squared over 8 plus 24.5 squared over 18. But not by hand. Stat, test, 2 sample t int, 2 sample t int. And the stuff's already in there. Nope. Negative 20.1, 48.1. Negative 20.1, 48.1. All right, anybody know how to respond to this? Anybody? Tim? Lindsay? Nope. Donovan? Nope. Mike? Nope. Mike? Nope. Carson? Nope. Natalia? All right. Good. Very nice, Natalia. Since 0 is in the interval, we fail to reject HO. All right, so Alba, finish it. Very nice. No evidence. Right here, we would say this. The teachers appear to have the same test scores. But it looks like, Mrs. Johnson's, the difference between Mrs. Johnson and Mr. Parisi is anywhere from they're 20 away such that Miss Johnson would be lower, and they're 48.1 away such that Miss Johnson would be higher. So it's in that fluctuating range. And then we solved the rest of them the exact same way. So inferences for two means that are dependent, these are like matched pairs, before minus after, or after minus before. These are matched pair scenario, which means like the independent one that we just did, it said independent, was like male minus female, Ms. Johnson, Mr. Parisi, or this drug minus that drug. Where this one is the same person is taking each drug. So let's look at an example here. All right, a medical researcher wants to determine whether a drug changes the body's temp. So here's the initial temperature of, all right, let's say that is Bree. So her initial temperature, not looking good, Bree, 101.8, all right? And then after she took the drug, she's down to 99.2. Still not looking good. All right, Amelia, 98.5, 98.4. All right, she dropped. Kelly Colville, right here. Who else? David Bass, all right, Andrew Chan, Bailey, and one of the Bens. I know I'm missing someone, I'm trying to. All right, tests that claim that the drug lowers the body temp. So what we're gonna do is we're gonna subtract all of these. So we would put them in the list, L1, L2. 101.8, 98.5, 98.1, 99. I wish I could pause the video, but I don't know how to do that, and I don't want to figure that out right now. Like pause it, have the numbers in here, and say, okay, here we are. 98.6. Oh shoot. 97.8. This one is 99.7. 98.6, 99. Oh, I really hope these are in here correctly. Okay, so for L3, I'm gonna do before minus, yeah, I'm gonna do before minus after. So before minus after. Okay, so really L1 minus L2 up at the top. Second 1 minus second 2. So here's all the differences. 2.6, 0.1, negative 0.1, 0.4, 0.3, 0.5, 0.1. So in this case, Bree's temp went down 2.6, Amelia's temp went down 0.1, Bass's temp went up 0.1. All right, so test the claim that the drug lowers body temp. So we do this. So it's not mu1 minus mu2, it's just a regular mu, but I'm only going to do a chapter 8 style test on that. My test stat is, you know, x bar minus mu s over radical n, like we did. So I have to find the x bar and the s for that column. So for L3, so stat, and then I'm going to go to t-test, because there's no two samples here. And I'm going to use the data that I have for L3. Otherwise, you'd have to do first var stats, find the mean, find a standard deviation, and then put that in there. Oh, Harper, what is going on up there? Or maybe that was Ashley crying. So there's the test stat. There's the x bar. So the x bar is 0.56 minus the mu, which is 0. The standard deviation is 0.92 divided by radical n. There were 7 people. And the calculator found this for us. P-value, that's 0.92. To find the p-value, we would do TCDF, because it's means, 1.6 to infinity, comma, degree of freedom, which is n minus 1. That was the degree of freedom before. And we don't times it by 2, and that's how we get 0.92. No. Yeah, 0.92. Oh, wait a minute. Wait. Lowers the body temp, so the difference needs to be higher. All right, I have to redo this. Gotta go back to t-test. Change that. Yeah, that's a pretty big p-value. 0.08. There we go. How come none of you guys caught that? Thanks for telling me. Yeah, so that would be 0.08. Since p-value is greater than alpha, we fail to reject HO. It doesn't look like that drug is really changing it too much, so there's no evidence to say that it's lowering. No evidence to say that this drug lowers. It looks like it is lowering, but that's only 7 people. If I were to test this on the entire population, it would be flip-flopping. I just happened to find randomly 6 people that it did lower a really small amount. Your body temp goes down 0.1, forget it, all right? It's not going to do anything. So if I had to do let's do a 98% confidence interval, it would be, well, it's just like the confidence interval from before. Sometimes they put D's here so that you know it's a matched pair. Same thing here, D's here so that you know it's a matched pair situation, but it doesn't matter. So x bar 1, 0.56 plus inverse t, 0.01, 6, degree of freedom, s over radical 7. It's 0.98, so 0.98, then 0.01, 0.01. That's how we're getting that. And then we're going to go stat test t interval. And I'm still going to use L3, but I'm going to change that to 98. There it is. Negative 0.54 to 1.7. So it looks like the drug is lowering at 1.7, but it also could be raising at 0.54. So anytime in research, you give the p-value, but you also give an interval for the viewer. All right, that's it. Done with this chapter.